students. Let's understand about stiffness modifiers. Providing stiffness modifiers for the analysis of beams and columns is a fundamental requirement for accurate and realistic structural modeling, especially in reinforced concrete design. Concrete is strong in compression but weak in tension, as you know that. Under external loads, the tensile stress in concrete exceeds its tensile strength, causing cracking. On-crack section analysis assumes certain concrete is perfectly elastic and resists tension, which is false after cracking. This leads to overestimation of stiffness, causing less deflection and more internal forces. Inaccurate prediction of crack width and spacing also is the result of this. So why stiffness modification is crucial? There are 5 reasons broadly it is crucial. First is realistic representation of the behavior of structural element. Using a crack section reflects the actual stiffness of the member in service condition. Using on-crack underestimates the deflection. Excessive deflection causing damage to cladding, partition, and other non-structural elements. And of course, it will be discomposed to users as well. Realistic internal force distribution is another reason we adopt stiffness modification. Using on-crack stiffness gives strong bending moment and shear forces so that there can be under-design reinforcement in critical regions, so it is unsafe design. Crack width control, also one of the reasons for that we adopt stiffness modification. Crack width calculation depends on the stress and reinforcement, which is only accurate if analyzed with crack section properties. Corrosion of rebars, reduced durability, and aesthetics issues are the consequences of not adopting modifier in that case. Seismic performance and code compliance is another reason we adopt stiffness modifier. Building models as on crack are unrealistically stiff, leading to incorrect seismic forces, and design would be against code compliance also. Because code has already introduced this sort of provision in codes, in Eurocode as well as American code and Indian code also. This is the optimum design method. Like cracking analysis allows for optimized designs, so higher material and construction costs will be reduced. After adopting this modifier. In programs like ETAP, SAP 2000 or Robot, you must input stiffness modifier like 0.35 for beams, 0.7 for columns. This is to reduce the gross moment of inertia properties of elements. These modifiers are code specified like ASC 41, Eurocode 8, and Indian code. For example, I have taken a couple of identical models except beams and columns are assigned with stiffness modifiers in one of them. In other ways, like loading and modeling wise, they are identical. As you can see, their base reaction for earthquake load EQX and EQI are same. However, due to modification factors, the internal forces are redistributed in cracked model and primarily reduced in beam and columns. Similarly, deflection for service loads like dead load and live load also differ in them. Crack model deflects more, which is realistic. We use crack section analysis because that's how reinforced concrete actually behaves under load. It's bridge between theoretical design and practical performance. Thank you for watching video. And if you haven't subscribed my channel 8, please subscribe. Thank you. It means a lot.